Right, so I'm going to be presenting some recent work from the Halflang project, which is all about exploring custom hardware architectures for supporting non-strict functional programs. And as has come up a few times already throughout the week, this is actually more of a re-exploration of a lot of these ideas. There's a lot of activity on this in the 80s and 90s, but we're kind of putting that in a modern context. So this talk is going to be almost exclusively about our new garbage collector. The goal there being we'd ideally have our collector run entirely in the background. And more importantly, not just in the background, we don't want to damage the performance of the useful work that's happening in our processor, the mutator. So if we can do that, we'll be very happy. So for some context quickly, we're kind of working to combine two separate research themes, right? So on the left, we've got software implementations of mostly concurrent garbage collectors, and that's all targeting stock CPUs. And on the right, we've got some cherry-picked examples of these custom hardware architectures for non-strict languages. So the ones we have cherry-picked here, the hardware architectures, they all kind of are based on one observation, which is that the von Neumann bottleneck is a real challenge for us as lazy functional programmers. Right? We do allocation a lot for immutable data structures and also for allocating thunks. Right? So we put a lot of pressure on that one serial connection out to a single logical memory. So in the 90s, Leonard suggested, well, maybe we should be looking at machines that try and widen that bottleneck a little bit. So working with very wide memories. If you've got these wide memories, then to make the best use of that, you probably also need a fancy stack structure where you can permute the top n elements. But that was the core idea there. And with the Halflang project, we've basically taken those ideas and really run with it. So we're prototyping this on an FPGA. If you were unlucky enough to look at our suite of benchmarks and evaluate them by hand on pen and paper, you could count the number of full function applications you're doing or full primitive operations. And we can kind of use that as a proxy for efficiency to some definition. So our processor there, on average, throughout our benchmark suite, performs 0.6 of those pen and paper reduction steps every single cycle, which we think is actually quite good. In fact, if you were to compare that to me running GHC with O2 on my laptop, for this dubious metric of efficiency, we'd come off 5 times better. But that's not the full story. Otherwise, you'd boot me off the stage, I'm sure. Our core, although it's really small, it also is clocked very slowly as a consequence of, well, lots of things, but some of these factors come from our architectural choices as well. So really, if you're comparing wall clock time with a modern multi-gigahertz CPU, we are going to be slower. In fact, I think really the etymology for our Halflang project, in retrospect, should have been, we've taken a perfectly good language and we've made it run about half as fast. But we do have all of these nice other properties. So in terms of energy efficiency, there's some interesting things. It is small enough so we can scale up to a sort of many-core solution, possibly on a single chip. And also for verification angles as well. One thing we do not have is a garbage collector. So we were looking over in the software world for inspiration there. And it feels like the best way to approach this is to try and do it concurrently on a sort of separate bit of hardware. So looking at the approaches people use in software, there's a really nice algorithm from UASA that does do this kind of in the background. But the observation that they make is for these von Neumann architectures, we're always going to have to insert some code into the mutator, slowing it down. And that's going to be serialized, and depending on where that is in a runtime system, it might be quite costly. But it will always be there in some form. So we've got a trade-off, right? We've got garbage collection approaches that either give us really good worst-case latency guarantees or quite good kind of throughput of our overall program, but never both. So for kind of modern attempts at this, a really nice example is this alligator collector, which is the basis for the non-moving garbage collector in GHC now. And it's a beautiful bit of engineering, so much so I think it's a good data point on just how much performance we can really get. But it still has this trade-off, right? So you get really nice latency performance there, but across the no-fib benchmark, compared to the Stop the World collector, it slows down a median of 21%, which is really something you have to think about. Our main observation is just that there is this trade-off. It doesn't seem to me like there's a way of escaping that with stock hardware architectures. So what can we do with a custom hardware architecture? And it turns out we can throw some pretty simple techniques at it and at least begin to approach a completely concurrent system that does not damage mutator performance. So our collector is called Cloaca. Assuming that the alligator collector was called that because it's low latency, it's snappy, then we've positioned ourselves at the other end of the gastrointestinal tract. And you can read whatever connotation you want from that. So just very, very quickly, so we're all on the same page about the terminology, let's look at non-concurrent mark and sweep, just so we get the terms. We can kind of model our system state as a directed kind of connectivity graph, and it'll be split over probably a stack and a heap. The goal of the mark and sweep collector is to traverse this graph, mark everything that's reachable, so we can then infer everything that is not reachable, and we can clean that up. So step one, we have to find something that is like trivially reachable. So we're just looking through the contents of our stack here. Any addresses we find, we remember, we outline it. So we're putting that on some like work list structure that we'll have to return to. And that's it. So the second stage will be marking. We traverse recursively that work list structure, and we fill in any node that we come across. If that node itself has pointers, we have to add those to the work list, and we just continue until the work list is exhausted. And finally, we do a sweeping pass that's a linear pass of the entire address space. Anything that's marked, we can reset for the next run. Anything that has not been marked, we know is unreachable, so we can free it. Okay, and that's the happy sort of non-concurrent version of this. There are challenges in making an algorithm like that that is resilient to graph mutations as it's doing its marking and sweeping. So what are those challenges then? Why is this a difficult thing to achieve in a purely software implementation? The first thing we have to think about is as the mutator is running when we're doing our collection, it might be adding new nodes to that connectivity graph. So the easiest thing we can do is assume for our garbage collection pass, those nodes will stay reachable. If that's not the case, fine, we can collect them on the next GC pass. So what we end up doing is in our allocation system, we have this new conditional saying, is the collector doing something dangerous here? If so, I need to say this is going to be reachable until at least the end of this pass. And we know that we're doing allocation all the time, so this is starting to look like it might cause trouble. Actually, slightly worse than that for allocation, we've now got a collector and a mutator kind of synchronizing on this shared graph, right? So we kind of would prefer to minimize the amount of mutation we do to that. So it's easier for us if we don't have a compacting or copying collector at all. But that means we have to be able to allocate in a very fragmented environment, right? We can't just use this bump pointer allocator using a sort of contiguous part of the address space. We'd really have to move over to something like a free list. So also in allocation, we now need to pop from some linked list structure, probably held in memory, probably also with some arithmetic accounting on the side. So we've taken the really nice allocation scheme and we've made it pretty nasty for such a common operation as well. The last point that's quite challenging is we also have to deal with graph mutation, right? Just because our surface language might be pure, it doesn't mean that this connectivity graph will be. We'll have to, at some point, be performing updates to it. The issue there is that update might destroy edges in our connectivity graph, and depending on where that falls during our garbage collection, that might also cause problems. So every single time we do an update, if the collector is doing something kind of sensitive, we might even have to do a round trip to the heap, look through its contents, see if there are pointers. We have to store them away somewhere for the collector to look at. Slightly less common than allocation, but still an issue. So one kind of more positive thing I'd like to say is beyond trying to address those challenges, there are additional optimizations that we might not necessarily get without something very expensive in a software world. So to describe one optimization we've got, we have to talk about how we do update avoidance in our graph system. So usually, if you fetch a node from the heap, you evaluate it to some normal form, you should then be worried about doing that work more than once. So usually, you'd commit that result back to the heap, overwriting the original. That costs us time and energy, so if you can avoid that, you probably should. In our case, we actually do that dynamically at runtime. One of the situations where you can avoid it is if you know that that node is not shared. So if it's totally unique, there's no possibility that that will be evaluated more than once, so you don't have to bother updating it. We do that sharing analysis dynamically at runtime, which is a very cheap thing for us to do in hardware. So every atom we're throwing about our system can take one of many forms. It could be a pointer into the heap, or it could be some function argument that's not yet resolved. Those are both tagged with a sharing flag. And throughout the execution of our program, we have to track those. If we end up duplicating one of these structures, we set the flag. But that is really just a one-bit reference counting system, right? That's this uniqueness analysis. It just happens we're doing it at runtime. So without changing the source code at all, we can actually just use that whenever we fetch something from the heap. If we know it's a unique reference, we can immediately free that address. So that trick by itself for our benchmark suite catches just over 50% of all of the garbage that we generate with a single conditional, which is a neat win considering we already had all of that hardware mechanism for update avoidance. Can you do this in software? Well, you know, there's certain languages that do have this uniqueness analysis, but if you're using a bump pointer allocator, that doesn't help you. You're freeing something behind you, but you can only allocate contiguously forward. So it would still be quite hard to implement in many other systems. So we've got lots of details on the architecture in the paper, But all I really want to show you here is how we handle that really nasty allocation scheme, because we have to actually do that twice every cycle to keep up with the mutator. So that is all to do with this bookkeeping memory we've got off to the right-hand side here, which is different from the heap memory. We use this bookkeeping memory just to store linked lists, essentially. So each node there can be a member of the free list. If the collector's marking, it might also have work list elements there. If not, it's marked or unmarked. The important thing is we have this memory in a slightly funny mode. So it's a read-first mode. What that buys us is when you write a value to an address, you have the side effect of reading the previous value that was held at that address. And that maps perfectly to our popping from a free list, right? We retrieve the old value containing the new, well, the tail pointer, so the new head of the list, while also overwriting with this conditional tag. So we can do that kind of atomically, and we have two interfaces into memory, so we get our 2 allocations per cycle. Just to give you an idea of what happens during one mark and sweep pass, we've got time going horizontally here, and we're interested in the mutator state. So is it running as it used to, or do we have to stall for some reason? So during route identification, we're mostly leaving it as is. So we actually have a separate interface into its stack, and we can walk up from the bottom, and it's only when we get very close to the top of the stack that we're worried about collisions. So we do have to pause the mutator, but only for, depending on the configuration, around 20 clock cycles. So for us, that's 100 nanoseconds-ish. So it's really not very long. For marking, again, we leave it running often all of the time. The only exception is if we manage to completely exhaust the heap before the marking finishes. At that point, obviously, we'll have to pause. We can try and avoid that, though, by setting how aggressive the triggering of our garbage collection passes are. So if we do that early enough and the heap is large enough, we should be able to complete a whole pass before we would exhaust the free list. And the same goes for the sweeping. So for results, we have one big caveat here. So we've got our test suite that's designed for our Heron core. If you take those same sources, because it is a Haskell subset, only recently is it syntactically a Haskell subset, we can look at the amount of allocation each benchmark's performing, and there are quite a few over 1 gigabyte, so that's approaching realistic for some definition. The caveat is, though, the working sets are tiny, and that is just to appeal to our current heap architectures. So we've got a very small core that maintains a very small local heap, and our plan for scaling that is through kind of replication into a distributed memory system, rather than scaling the heap controlled by one of these cores. So even outside of that, we don't see any reason this shouldn't scale, certainly not worse than a software implementation, but that's not what these results are really showing. So we're working only with quite small working sets here. The first thing we would want to look at is the worst case pause time introduced by the collector. So we've got GHC, again, running on this laptop in front of me. We're plotting the worst case pause for the collector, and we've run that for all of our benchmarks, and for each benchmark we have a couple of different heap sizes. So on the GHC side, we can kind of see, oh, I should mention actually, this is with the default GHC collector, and we've done that in GHC's favor because these are such small working sets. programs, we don't really exercise the oldest generation, that's collector very much, and that's the only part of the non-moving collector that is concurrent. So to get the best results from GHC with these examples, we're using the stop the world collector. But we can kind of see the trade-off between latency and throughput here, because you'd expect as you increase the heap size, you'd trigger fewer garbage collection passes, so the overall time you spend doing collection is reduced. But also the latency tends to increase as well. For the Cloaca implementation, we've got quite a different trend. So we are essentially, with a big enough heap, down in the noise. If we have a heap that's approaching the same size as the peak working set, sure, we do spike up a little bit, but if you look at the y-axis, then we're not doing too badly. Similar set of plots for the overall overhead. So this is the percentage of the total wall clock time that was spent only doing garbage collection. There was no useful work being performed. On the GHC side, you can see that is trending the other way, right? That's where that trade-off lies. But for us, it's exactly the same trend, right? If you can come up with some heuristic, say if your heap size is 3 times bigger than your working set or more, you're probably going to be down in the noise for the overall GC overhead, which is quite nice. We don't have any static guarantees there, but you can see the trends. So just to wrap up, we've seen that concurrent garbage collection feels like it should be promising low latency collections and also maintaining quite high throughput. But when we're implementing that with stock CPUs, it's actually really hard to maintain that throughput aspect because we're having to insert this set of write barriers and some synchronization stuff, and that's all sequentialized. If we just throw some really quite simple hardware tricks at it, most of those just reduce to being a single cycle operation. And more concretely for our implementation, often you can do an entire garbage collection pass with about 100 nanosecond delay. And the nice little cherry on top is we already had 1-bit reference counting, but we just called it something else. So that will catch about half of all the garbage for our benchmarks, even without doing these mark and sweep passes, which is a nice little win. And that's me.
We have time for questions.
Are your dual port read first memories like ordinary dual port memories? Because they're much more expensive than single port memories.
So that is true, but we're doing all this prototyping on FPGAs. So we're really only offered, well, they're physically already there, right? It's a resource that's available to us, so we're choosing to.
But if you wanted to make an ASIC or something like that, they would take up a lot more space then.
Yes. So if you're making an ASIC, that becomes a consideration. And there's actually the Cephalopod project at Chalmers that took those sorts of considerations into mind because they weren't targeting FPGAs to start with.
Hey, a really nice talk. So I know it's not the direction you're thinking of going, but I'm curious if you were to try attaching a large gigabyte-sized memory to this, what would be the challenges in getting good performance out of this with a large heap?
So I think the garbage collector would cope with that fairly straightforwardly if you kept that same total heap size divided by working set metric. The difficulty is in the actual reduction part of the core. we've got an IFL paper on it. It's a non-pipelined design, so it needs single cycle access to the stack and the heap. So then we need all the normal machinery of like caching and prefetching, and that stuff would be very important for a real world version, but to us, it doesn't seem like where the interesting research questions lie. So.
Okay, makes sense. Thanks.
Oh, also we're using Clash.
So, are there any plans to move to DRAM? Because then you would definitely use your dual ports, because you can't even do single port then, because it's just one data bus write only or read only.
Yes, so
what happens then?
So, kind of similar to the last question, we aren't planning on exploring off-chip memories yet, because the FPGA we were targeting, we're occupying like less than 2% of. We can't really scale up a single heap memory without degrading the clock frequency. So the obvious thing to do is first try and actually use all those FPGA resources by like scaling out into a multi-core distributed memory system. So we were planning to explore that before looking at any sort of off-chip memory, DRAM or otherwise.
Okay.
Let's thank Craig again.